In this question, we've got two walkers, and we've got this walker and we've got this walker, and they start off at, if we take this to be an origin, they start off at minus 5i is walker A, and minus 20j, so down here, is walker B. And walker A is walking east at 10 kilometres an hour. Off he goes, doot, 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 like that. And walker B is, what's he doing? He's walking at 20 kilometres an hour. I actually think people can't walk that quick, but these were ships in the original question in the textbook. But I'd already done one on ships, so I wanted to do one on walkers. So now they're walking really, really fast. So are they going to crash? Don't know. But what we're going to find out is what is the position vector of A relative to B, and what does that even mean, and what's the distance between A and B at any given time. So at the moment they are this far apart, and then if he walks that way a bit and he walks that way a bit, they're going to get closer together. They might even crash, not sure. And then they're going to get further away again, like that, as they walk away. So let's get a position vector of each of the walkers. So walker A at time t is at his start position, minus 5i, and then he's done t lots of his velocity vector, and his velocity vector is 20i, because he's moving 20 kilometres per hour in this direction, 20i. And walker B starts at minus 20j, and every hour he does 10 in the j direction, so that's where he is. So what does A relative to B mean? So question one we could ask, where is A? A is here, A is here, A is here, A is here, A is here. But that is relative to this origin. Minus 5i is minus 5i relative to this origin. So if you're at the origin and you're looking at A, you're at minus 5i, minus 4i, minus 3i, minus 2i, 2i, 3i, 4i. But A relative to B means where is A if I am person B? So in this, where they are at the moment, A, the position of A relative to B is more like minus 5i plus 20j. Minus 5i plus 20j is where A is relative to B. So when we say A relative to B, what we mean is B to A. So B is looking at A, and we know that that's A minus B. We did that in the last video. So walker A is at minus 5i plus 20ti, and walker B minus is at minus 20j plus 10tj, which altogether is minus 5 plus 20ti plus 20 minus 10tj. I think I got my minus signs right there. So that's the position vector of A relative to B at any given time. So at the beginning, when t is 0, minus 5i and plus 20j. And then as t changes, and this walker goes this way, this walker goes this way, the vector connecting them also changes, but it's always given by this. So this is the vector from B to A at time t. And hence the distance between A and B. Now the distance between A and B would be the length of this vector. So it would be this bit squared plus this bit squared, square rooted. Nice little application of Pythagoras. So that is minus 5 plus 20t squared plus 20 minus 10t squared. And that would be the distance. Square rooted would be the distance. So that would be the distance squared. I'll just expand that out. So we get 25 minus 100t plus 400t squared plus 400 minus 400t plus 100 is d distance squared. That should tidy up a bit more. Let's divide everything by 25 and tidy it up. So I might have gone wrong, but I make it 16t squared minus 20t minus 11 is d squared. So the distance between them is the square root of that. Now we know that walker A and walker B are going towards each other for a bit, like this, and then getting further away. And if they are within 15 kilometres of each other, if the distance between them is 15 kilometres or less, then their walkie-talkies will work. So let's see if we can work out whether or not that's going to be possible. We know that the distance between them is always, well, the distance squared, 16 squared minus 20t minus 11. Now, that distance, that's a quadratic, isn't it? So it's a positive quadratic, so it's looking something like this. And this is the distance between them, and this makes sense. The distance between them is getting smaller and smaller and smaller as they come together. And then there's a closest point, and then they get further away again. So what we're looking for is, when are they as close as possible? Now, it's a quadratic, so I could complete the square to find the turning point, but probably easier than that would be to differentiate it. So I'm going to differentiate this function, so I get 32t minus 20, and then I will make the gradient, the derivative, equal to 0. Then I can solve this. 5 over 8. So time 5 over 8 is when they are going to be as close together as they ever possibly get. So let's see now how close they actually are at time 5 over 8. So at time 5 over 8, the distance squared would be 16 times 5 over 8 squared minus 20, lots of 5 over 8, minus 11, and that gives me a distance of, right, well apparently I get a distance of minus 17.25, so a distance squared. So I think I might have gone wrong. What I'm going to do is I'm going to not square root that because it's a negative number, and I'm going to ask you to find my mistake, and you can find the actual shortest distance. Now, if that smallest distance is less than 15, then we know that they get close enough to use their walkie-talkies. And if that distance is bigger than 15, then that's the closest they get, then they never get 15 or less kilometres distance between them, so they can never use their walkie-talkies. So good luck finding my mistake and correcting it.